This is APAB Calc. We're doing Intro to BC Calc, topic 2, which is partial fraction integration. So here we have example 2, which is in the packet, 2x squared plus 3x plus 2 all over an x cubed plus x. So again, hints that this is not u sub, and I know it's not listed in the packet, but just to show you the difference. See how the denominator is an x cubed plus x? So if you were to derive the denominator, right, if you called the denominator u, your du would be 3x squared plus 1. If the top of this fraction were a 3x squared plus 1, boom, this is u sub. Or even if the top of this fraction were double that, like a 6x squared plus 2 or something, right? Then it would totally be u sub. The difference here is that there's no way that deriving this gives me the stuff on top, right? And that's sort of the thing that you need to keep in mind. So knowing that, let's do some partial fractions decomposition. So I'll inch over here, right? So we're going to do the partial fractions decomp. I would suggest that you do it separately from the integral because it makes your life a lot easier to do the pre-calc portion separately. So I have a 2x squared plus a 3x plus a 2 on top of, if I factor this denominator, I'm going to have an x that comes out and I'm going to get an x squared plus 1. So what that means is I have a linear factor and I have a quadratic factor, right? So when I set up my decomposition, I'm going to have an a on top of the x because I'll have a constant over a linear factor, but I'm going to need a bx plus c on top of the quadratic factor. I need a linear numerator on top of a quadratic factor. Again, if you're at all rusty on this, please go back and watch the pre-calc videos on how to do partial fraction decomposition. So then my goal is to get the same denominator for each of these. The common denominator should be identical to the original. So when I do that, it's going to mean that I multiply my a fraction by the whole quantity x squared plus 1 over x squared plus 1, and then I multiply this entire bx plus c times an x, and this entire x squared times an x, and then I'll get identical denominators on the left-hand and right-hand side, which gives me the ability to just pay attention to the numerators because all of the denominators of the fractions are the same. Mathematically, what you're really doing is multiplying the entire equation by this x times an x squared plus 1, but mathematically it's kind of easier to just be like, cool, so the numerators are equal. All right, so here's the issue. Usually when we do these problems, we do what we call clever substitution, right? I would pick an easy thing that would knock out this set of parentheses, and then I would plug it in for x, and boom, I can find the values. The problem is that x squared plus 1 is only going to get knocked out by a plus or minus I, and really you don't want to start introducing imaginary numbers into this. Now, I can knock out both b and c if I plug in x as 0, right? And x as 0 would knock out this entire expression and leave me to find a. So that's what I'm going to do. I'm going to start with some clever substitution. I'm going to go ahead and plug in x as 0, and on this side I'll get 0 plus 0 plus 2. And on the other side, everybody but the a gets knocked out. So I end up getting a is 2, and that's great, because unfortunately it's going to be slightly harder to find the other ones. Now, there are two ways to go about finding the other ones. Option 1 is to just pick two different random x's and essentially get a system of equations, and that's fine. But there is another interesting option. So when I was a kid in high school, I didn't actually know this clever substitution option. The option that was presented to me was a little bit different. So let's walk through that over here. So what I learned instead was to write out this entire equation, so 2x squared plus 3x plus 2 on the left-hand side, right? And on the right-hand side, to distribute everybody, now I'm going to go ahead and know that that a is a 2, so that's going to make my life a little bit easier here. So I'm going to get a 2x squared plus 2, and when I distribute the x, I'm going to get a plus bx squared plus cx. So an interesting thing's going to happen, and it would still have worked even if I had kept that a as an a, like if I had not done this first. On the left-hand side, because this is, and here's my right-hand side, right? On the left-hand side, because this equation has to be true for every x ever, the stuff on the left-hand side that is in front of an x squared has to be the same as the stuff on the right-hand side that's in front of an x squared. So I can essentially make an x squared coefficient equation. And I can say that on the left-hand side, there's 2x squared, and on the right-hand side, there's a 2x squared and a bx squared. So the left-hand side is 2, the right-hand side is 2 plus b. Oh, look, b must be 0. And then for x, I can say, oh, there's a 3x on the left-hand side, and on the right-hand side, the only term that has an x is the c, so cx, so 3 must be c. And then the numbers would have to be 2 equals 2. Those are the only constants. But keep in mind that actually would have been 2 equals a if I had not known a, right? So just to go back for a sec, actually, if you wanted, you could even go back and pretend we didn't know this a stuff. You can see that even if I hadn't done this stuff over here, even if I hadn't found a using the x equals 0, I would have ended up with 3 equations. 2 equals a plus b, which I don't know a or b at that moment. If I hadn't done 3 equals c, well, there's c, it's done. And 2 equals a, which I could then back substitute to find that b is 0. So either way, you end up getting that if we come back up here, I have that this is the integral of a, which was 2 over x, plus my b x plus c, which is going to be a 0x plus 3 over an x squared plus 1, all with respect to x. So now we're at the point where we can go ahead and integrate. So again, all of that partial fractions decomposition is technically an Algebra 2 / pre-calc skill, depending on if you had me for class, you learned it in pre-calc. If you were coming from somewhere else, you might have learned it in Algebra 2. So if I look at these two pieces of the integrand, though, they're actually both really straightforward. 2 over x dx is definitely just a natural log with a 2 in front, right? And 3 over x squared, now that one's going to be an arctan, right? So just a reminder of how arctans work, right? So if I integrate du over u squared plus a squared, it integrates to 1 over a arctan of u over a plus c, right? So in this situation, my u is x, my a is 1, right? So what's going to happen is I'm going to get, this guy's definitely a 2 natural log of the absolute value of x, right? And then this guy is exactly the arctan formula, just with a 3 in front. So this is going to be 3 arctan or inverse tangent. It doesn't matter whether you pick arctan or inverse tangent. They're the same thing. So 3 inverse tangent of x over 1, but I can just call that x plus c. So when you have a quadratic factor in these problems, you often will end up with an arctan, just so that it's on your radar. You're not usually going to see an arcsine or an arcsecant in these situations, and the reason for that is that both of those formulae have roots. And you'll notice that that we don't have roots in these because we're talking about rational functions, where the numerator and denominator are both polynomials.